Okay, yeah, I guess I can start.
Cool.
All right. All right. Hi, everyone. My name is Sharhad, and today I will be presenting the paper on detecting 21,000 classes using image-level supervision. The presentation is by myself and Eluid, but unfortunately he could not be with us today. So I will do my best. So before starting, I'm just going to go over the agenda for today's presentation. First, I'm going to do a little bit of introduction of the problem. I'm going to go over some of the previous work. I'll also go over the data sets that are used throughout the paper. I will also talk about the paper's contribution to the problem, and I will go over some experiments and results. And finally, I will do a little demo. So for the demo, I have some images that I'm going to be running through, but I want to make it a little more audience engaging. So if anyone wants to send in any images, they can send it to me on Slack, and I will try to accommodate you guys. All right, so introduction. So object detection, when you have an image like this, object detection consists of two things. First, you have to find the object, for example, the lion here. And then the second thing that you have to do is you have to label it. So traditional methods couple these two subproblems and thus rely on box labels for all classes. However, detection datasets are much smaller in overall size and in terms of the number of objects of classes than image classification dataset. For example, we have the Elvis dataset, which is large vocabulary instance segmentation. This dataset has 120,000 images for about 1,200 classes. We also have open images, which has about 1.8 million images for 500 classes. But these images or these data sets do not have enough images or enough classes. In comparison, if you look at ImageNet, which is a 10-year-old image classification data set, this has over 14 million images for 21,000 classes. So this paper, what it does is it proposes a method called detic, which stands for detector with image classes. And it uses image level supervision in addition to detection supervision. So we have modern region proposal networks, or RPM, which already can localize many new objects using existing detection supervision. Since they can detect it, what we need to do is classify and label it. So that's what this paper focuses on. It focuses on the classification subproblem and uses image level labels to train the classifier and broaden the vocabulary of the detector. So now let's talk about some of the past work. So standard detection requires good ground truth labeled boxes, and they cannot leverage image labels. So in standard detection, you need to have each individual object, as you can see here, you need to have each individual object in a bounding box with a label. But as discussed in the previous slide, there isn't a lot of data available for these kind of detectors to train on. So how do current methods get around this? So weakly supervised methods like YOLO 9000 or DLWL, which stands for Detection for Low Shut Classes with Weakly Labeled Data, they use image level labels by assigning them to the detector's predicted box. They detect objects in an image. So what they do is they detect object in an image, for example, here. So in this image, they detected this person, the second person, and the third person, as well as this ball. So they detect objects in an image, and then they assign labels to them with the highest confidence score. So after they detect these objects, they try to assign these labels to these boxes. And then they use these as pseudo ground truths to train their object detectors. Unfortunately, this assignment is extremely error prone, especially for large vocabulary detection. And this assignment requires good initial detections, which leads to a chicken and egg problem. So we need good detectors for good label assignments, but we need many boxes or many images with many boxes to train a good detector. So what does this paper do? So detic what it does is it omits the label to box assignment and supervises all image labels to the max size proposal. So what do I mean when I say max size proposal? So max size proposal is when we already have RPNs which can detect the different objects in an image. So what max size proposal does is it takes all the different objects that were detected, puts them together, and draws a bounding box around the entire thing. So if you guys remember in the past, in this example here, it detected 4 individual objects. And so what max size proposal does is it draws a bounding box around everything. And after it draws a bounding box around everything, it assigns all the labels relevant to the image to that bounding box. So to summarize, they find all the objects of interest in the image, draws a large bounding box around it, which is called the max size proposal, and then assigns all the appropriate labels to that one bounding box. So before I go into more details about the contributions of the paper, I would like to go over a few data sets that this paper uses. First of all, I already talked about LVIS, which stands for Large Vocabulary Instance Segmentation. It has about 100 or 1,200 classes for 120,000 images. And these images are divided into 3 categories. So you have frequent, you have common, and rare, based on the number of training images. So when you see LVIS-all, it refers to all the images in the entire data set, so all 3 categories. LVIS-base, this refers to the LVIS dataset with the 317 rare categories omitted. IN-2K, that stands for ImageNet 21K. So they use 2 datasets for image supervised data. That's ImageNet 21,000K and CC, which stands for conceptual captions. So as I already mentioned, ImageNet 21 contains 14 million images for 21,000 classes. And for ease of training and evaluation, most of the experiments use the 997 classes that overlap with the LVIS vocabulary. And this is donated as IN-L, which stands for ImageNet LVIS. And conceptual captions is an image captioning dataset that contains about 3 million images. And they extract image labels from the captions using exact text matching and keep images whose captions mention at least one LVIS class. So there are also a couple more datasets that are used for evaluation purposes, and I will talk about them when we get to that. Okay, so let's talk about the contributions of the paper. So most object detectors, they follow a 2-stage framework. The first stage, it's called the Region Proposal Network, RPN for short. And what it does is it takes the image and it produces a set of object proposals. So in this example here, the object proposals are denoted by F_J down here. So what the second stage is, it takes these object features and it outputs a classification and refined box location for each box or for each object. So if you look on the right side here, the classification labels are the labels percent, sports ball, and background. And the refined box location is down here on the bottom right, where it defines the exact bounding box for each object. And as you can, and if you guys see capital W and capital B, those are the learned weights of the classification layer and the regression layer, respectively. So overall, traditional methods of object detector, they have 3 losses. One loss comes from the region proposal network, one from the regression, and the third one from classification. So the contributions of this paper focuses on improving the classification in the second stage. All right, so how does this paper work? So first of all, we start with 2 data sets, as I mentioned before. The first data set is a data set of all object detectors where all the image have bounding boxes around them. And the second data set is a classification data set where you have an image with a label, right? So during training, what they do is they create a mini batch by taking images from both these data sets. For images with box labels, so images from the detection dataset, they follow the standard two-stage detector training that was described in the previous slide. For image level data, what they do is they ignore all proposals from the region proposal network, and they start by using the entire image as one big proposal. And from the data set, they already know that that image has K labels K labels assigned to it. And they are also able to extract all the important features from that image. Once once they say that the entire image is a proposal and they have all the features and the labels, what they do is they apply a classification loss to its region of interest features for all classes in that image. The loss is, I'm not really going to go into like the technical details, but it's basically a binary cross entropy loss with a sigmoid activation. So this image you see here are the losses. So if you guys remember in the previous slide, I said that for detection data or for detection images, there are three losses: one from the region proposal network, one from the regression, and one for the class or for the classification. So whenever they have an image from the detection dataset, they use a combination of these three losses. And whenever they have an image from the classification dataset, they use a loss called max size, which is the binary cross entropy loss that I just described, which is the main contribution of this paper. And lambda here is a constant of, I believe, 0.1. So
sorry to interrupt. What is the regression loss? I am not a computer vision person, so this is new to me.
So regression loss is the, let me just go back here. Regression loss is the loss that comes with the refined bounding box. So if you see B here, right, that's the refined box location for each object. And when you're trying to refine that, you have a loss function associated with that. So that's what they mean when they say regression loss.
I think we have to predict the coordinates, I guess, in that. That's why we have to.
Yeah, so they put the coordinates of the box.
Coordinates, we have to predict coordinates. So regression term comes in.
Yes, exactly. Anyways, as I was saying, yeah, so the main contribution of the paper is this loss max size, which is for all images that come from the classification dataset. Okay, so also note that W, which is the classification weights, which I mentioned in the previous slide, they are shared between both the detection and classification data, which greatly improves detection performance. Another thing to note is that initially this paper started out by saying that for classification images, we will use the entire image as the proposal size. But later on, they discovered that if they use the detectors and just locate all the objects in the image and thus draw a max size proposal around all the objects of interest in the image, they found that they found that performance gets better. So in all the experiments and results that we see, they will be using max size proposal as their loss. Okay, so now that we talked about their contributions, I'll be going over some of the experiments and results that they performed to validate their methods and contributions. But before we get into the experiments and results, I'd like to go over a few terms with you guys, so which you will be seeing in the slides to come. First is WSOD, which stands for Weakly Supervised Object Detection, and it trains object detectors using just image level labels. Second is a term called Open Vocabulary Object Detection. And this is when you aim to detect objects that are outside the training dataset vocabulary. And thirdly, another term is Large Vocabulary Object Detection, which is when you're trying to detect over 1,000 classes. A few more things to go over before we get into the results. So the team, before they demonstrate their method and contributions, they establish a strong baseline on the Elvis dataset to demonstrate that their contributions improve results. So whenever you see the term box supervised, that's what they mean by the baseline baseline results. So the baseline only uses supervised bounding box labels, and it's trained on the Elvis dataset. Yeah, it uses a supervised bounding box labels. They use CenterNet 2 detector and ResNet 50 backbone for all the box baseline tests. Another thing that you guys will see a lot is called MAP, and this stands for mean average precision, which is a popular metric in measuring the accuracy of object detectors. And basically, without going into much detail, it's basically the area under precision and recall graph. Precision is the measurement of how accurate your predictions are, so the percentage of your predictions that are correct, and recall measures how good you find all the true positives. And yeah, as I mentioned, it's the area, mean average precision is the area under the precision recall graph, and basically, higher the map value, the better the results are. And for every experiment that you guys are about to see, they tested it 3 times and then took the average map. Okay, so the first experiment that we are going to be looking at is they explore how to use different image level supervision. So if you guys remember from the dataset slide, I mentioned they used Elvis with ImageNet L dataset. They also use Elvis base with conceptual captions, and they use another dataset called Open Vocabulary COCO. So they experiment with these 3 settings. And these three settings differ in the number of objects and the number of images or number of image labels per image. So Open Vocabulary COCO, it's another data set. It's a much smaller data set with about 48 base classes and 17 rare classes. But the difference between COCO and ImageNet is that COCO images are designed to contain many or multiple objects per image, whereas ImageNet images mostly contain 1 object per image. So the first 2 lines that you see are the box supervised, which is the base results that I mentioned in the previous slide, and they have relatively okay scores on the different data sets. Self-training is a method that was introduced in a 2020 paper. It's called a simple semi-supervised learning framework for object detection. And they have the scores for those methods as well on the different data sets. Number 5, 6, and 7, those are weakly supervised methods. So the first one, WSDDN, it's a paper on a weakly supervised deep detection network presented in 2016. The second one, DLWL, it's improving detection for low shot classes with weakly labeled data, presented a couple of years ago in 2020. And the final one, predicted, that's the YOLO 9000, which was presented in 2017. And number 8 is the detic method that this paper proposes. And as you can see, all across the board, detic outperforms all the different methods on all 3 different data sets. One thing to note is whenever you see map and then novel down here, that refers to the rare classes that were taken out from the Elvis dataset for testing purposes. So yeah, as you guys can see here, for different image level supervision, detic outperforms all the methods that are out there. So moving on to another experiment. So now we use detic to train open vocabulary object detectors and compare them to the state-of-the-art method. So currently the state-of-the-art method is WILD, which is a paper on zero-shot detection via vision and language knowledge distillation. And as I mentioned, open vocabulary object detector, it aims to detect objects outside of training vocabulary. And this experiment that you're about to see is trained on open vocabulary Elvis. So WILD is a method that uses clip embeddings for open vocabulary detection, which is also the same thing that detic uses. So clip embeddings is clip is a neural network which efficiently learns visual concepts from natural language supervision. So let's say if you have an image with a caption, clip learns to find image labels from that caption. And yeah, as I mentioned, it is tested on Open Vocabulary Elvis. And as you guys can see, for almost all the methods, detic outperforms the state-of-the-art WILD. So WILD has three different versions. So WILD text is more or less the same as the base level box supervised baseline, which I mentioned in the previous slides. WILD, which is the main method, it uses knowledge distillation from clip visual backbone. And WILD Ensemble is kind of the best of the two methods, WILD text and WILD, and it provides improvements on both those methods. But as you guys can see, detic outperforms all three of these methods on almost all cases, except for the frequent case where WILD text does better. But this gives you an idea of how detic performs when it is compared to state-of-the-art open vocabulary object detectors. So moving on, now we are going to compare detic with prior works on Open Vocabulary COCO benchmark. So as I mentioned before, Open Vocabulary COCO has 48 base classes and 17 novel or rare classes. And COCO images are designed to contain many objects per image, as opposed to ImageNet. And the state of the art is currently a method called OVR-CNN, which stands for Open Vocabulary Object Detection Using Captions. And this is both detic, and detic was trained for this specific data set following following the guidelines of over CNN. So it was trained with faster RCNN detector with a ResNet 50 C4 backbone. And following OVR-CNN, they also use COCO captions as image supervised data, and they convert captions into image labels and use both image labels and captions as supervision. So as you can see, over CNN, which I mentioned, is performs the best with 39.9 map on all the box or all the classes, 22.8 on novel classes, and 46.0 on the base classes, which is the common classes. And as you can see, detic outperforms over CNN on all the different classes. It also outperforms all the other methods that are mentioned here. It only gets beaten out by the base class for just the common image labels. All right, so moving on. Now we are going to see how detic performs given different backbones. So box supervised was the method that I talked about using baseline, and the two different backbones that we use here are ResNet 50 and SWIN-B. So this result or this experiment shows that detic outperforms box supervision as well as many of the different methods, regardless of the backbone that they use. So as you can see, ResNet 50 backbone outperforms the ResNet 50 backbone of the baseline, and SWIN-B outperforms the baseline model trained on SWIN-B backbone as well. And these 6 methods down here, they all use heavy networks as their backbones, and detic still outperforms all of them, or almost all of them, except for seesaw loss for the frequent cases. So moving on, I'm going to be talking now about another method called Mosaic OS and how it compares to detic. So Mosaic OS is a simple and effective use of object-centric images for long-tailed object detection. It was proposed in 2021, and it also uses image-level annotations to improve Elvis dataset. So in addition to using ImageNet LWIS dataset, it also uses additional image searched from Google as image supervised data. And it uses mask RCNN as a detector and ResNet 50 as the backbone. So Detect was also trained in the similar situation or with similar cases with mask RCNN as a detector and ResNet 50 as backbone. And as you can see, it outperforms Mosaic OS for almost all cases except for the frequent case, but it comes very close to the result. And this is an amazing result because Detect greatly improves the results, all at the same time being easier to train. Because as you can imagine, Mosaic, which uses additional data from Google, would definitely be a lot harder to and time consuming to train. Next, so I'm going to be talking about how detic performs when it is trained on the full 21,000 classes of ImageNet. And this is done by using SwinB, which as you guys saw was the stronger of the backbone. And since there are no direct benchmark to evaluate detectors with such a large vocabulary, what they do is they train Detic using the 21,000 classes of ImageNet, and then they evaluate the detector on new data sets without any fine tuning. So they evaluate on two large-scale object detection datasets. So one is Objects 365, and the other is Open Images, both of which have around 1.8 million images. So, and as you guys can see, Detic with their 21,000 labels outperforms or performs amazingly for all the cases on both the data sets, and it does greatly compared to the baseline scores. All right, so now the second last experiment that I'm going to show. If you guys remember, when I was talking about their contributions, I talked about different losses that the paper proposed. So some of these losses are object score. The second one is image box, where you take the entire image to be your proposal size. And the third one is max size, where you have a max size proposal by focusing only on the objects of interest in the image. So as you can see on all the three data sets, the last one, ZS COCO, is just another way of saying open vocabulary COCO data set. And as you can see, regardless of what loss function they use for training their classification data, Detic outperforms the base model on almost all cases. And the max size loss function, which is the function that they use for all the training purposes, performs the best out of all the three loss functions that were proposed. And finally, the team wanted to make sure that Detic performs well regardless of the classifiers that were used. So what they do is they use different classifier weights for W. So their main open vocabulary experiments use a classifier called CLIP, which I mentioned before, but they also wanted to make sure that it worked well regardless of the classifier that they used. So they tried it with 3 other classifiers as well. And as you guys can see, it still outperforms the box level or the baseline scores by quite a bit. So yeah, that is it for my presentation. I am now going to stop my screen share and I'm going to start the demo. So do you guys have any questions? No? Okay.
What exactly is the backbone?
So backbone is I guess it's something that's a pre-trained neural network that is used to that has a pre-trained weights with or it's pre-trained on the data set that they're using. I'm not 100% sure if I know. So let me know if you guys can see my screen. Yeah, okay. So on the left, you have an example input image, and on the right, you have what the output is. So I already ran it for this image, but so as you guys can see, it detects the different things in the image. So for example, it detects the street light, it detects the airplane, it detects the cars and the trucks, and at the same time, it also detects the wheels as well. So if I try another image, so let's say this one of a car, right? So if I submit it, it takes about 7 seconds, I think. So yeah, as you guys can see, this is how it detects the different things. So it detected the car. It also predicts a confident or a score of its detection. It detected the car, it detects the wheels, it even detects the bolts in the wheel hub of the car. It detects the tail lights, reflector, rear view mirror, and everything. So as you guys can see, it performs really well when there's one image or one object in an image. So yeah, let's try a few more. So let's go on this one here. So yeah, this is an image with a lot of cars, a lot of buildings, a body of water as well. And as you guys can see, it relatively detects most of the different things. So it detects cars, even detects license plates, detects a silo in the background, a boat on the side, and things like that. So let's try another image, sports image. And yeah, as you guys can see, this is the output of such an image. Yeah, so it detects the different things in the image, like shorts, socks, shoe, hockey stick, even the ball, person, things like that. Let's try another image. So let's say of this person that's walking. It's taking a little longer than I thought. Okay, I don't know why this is taking too long, so let's try another one. Okay, I seem to have broken the presentation or the demo. So yeah, I guess I'll just stop here. It's an online demo, so that I already put the link on the presentation. So if you guys want to check it out, you can. I will end the presentation here, and if you guys have any questions, we can go over them. Thanks.